Total Productive Maintenance, or TPM, is a group of techniques that are used by companies to help ensure that every machine in a production process is always able to perform its required tasks. TPM maximizes productivity by using planned maintenance activities to identify and correct inefficient processes, equipment, or operating procedures. The goal is to reduce equipment-related waste and aims for zero equipment breakdowns. TPM is a philosophy as much as a program. To achieve its goal requires a commitment from everyone, from equipment operators to maintenance technicians and managers. TPM also involves systematic training of employees to improve their knowledge of the equipment they use and strengthen their skills. Total productive maintenance is important for several reasons. It corrects inefficiencies in processes or equipment and prevents breakdowns, which can be costly to a company. TPM promotes a positive work environment by encouraging people to think of ideas for improvement, providing operators a sense of ownership and responsibility over the equipment they use, and improving working relationships between operators and maintenance personnel. There are several elements of TPM. Some of them are listed here. One element of TPM is preventive maintenance, or PM, which is the process of performing routine maintenance and periodic component replacement on a machine based on a predetermined schedule. The intent is to prevent unplanned downtime due to failures. The PM schedule is based on the equipment manufacturer's recommendations and the machine's history of previous failures. Typical manufacturer recommendations include tasks such as tightening, lubricating, and cleaning. These tasks extend the lives of the machine components. Tasks are often organized into frequency categories by shift: daily, weekly, monthly, and so on. A PM schedule includes periodic replacement of various components when they are nearing the end of their expected life cycles, but before they have failed. Components commonly replaced on a periodic basis include filters, fluids, belts, and bearings, to name a few. The time for replacement is based on the machine's history of component failure or the manufacturer's recommendations. The goal of PM is to avoid unexpected machine breakdowns and extend the life of the machine. Performing maintenance on machines after they have broken down is often expensive. The activities of preventive maintenance are guided by three principles. Maintain equipment at normal operating conditions. Discover potential problems as early as possible. And respond promptly to problems. It is important to keep machines operating at normal conditions to prevent breakdowns. Many early component failures are caused by machines operating outside of normal conditions, such as above normal oil temperature. Preventive maintenance involves performing tasks such as tightening, lubricating, and cleaning on a routine basis to extend the life of a machine. Machines should be monitored and adjusted when needed so they operate at an optimal level. The equipment manufacturer's recommendations regarding approved accessories, speed settings, and other operating parameters should be observed. Machines should not be operated in a manner that causes them to be overloaded or used with unapproved accessories. Doing so can shorten the machine life and cause unnecessary breakdowns. It is the operator's responsibility to call attention to anything that looks, sounds, smells, or feels wrong with the machine, even if the machine is not yet malfunctioning. The maintenance department should conduct periodic tests to prevent problems. Some common tests are taking pressure and temperature readings, performing oil and vibration analyses, and doing historical and statistical analyses. If a machine abnormality is discovered, the operator should respond promptly to correct the problem to avoid a possible breakdown. The operator should work with maintenance to determine the cause of the problem and to develop controls or process improvements to prevent the problem from occurring again in the future. Predictive maintenance, or PDM, is the process of performing inspections and tests to determine the current condition of the machine. Predictive maintenance is also referred to as condition monitoring. The intent of this process is to detect problems early, before the machine actually fails, and enable the technician to correct the problem before a major breakdown occurs. Predictive maintenance uses a number of tests to check the condition of the machine. These include vibration monitoring, oil analysis, acoustic monitoring, and thermography. Vibration monitoring checks the amount of vibration at various points on the machine to ensure that the levels are acceptable and to detect problems that could lead to failure before they actually fail. The vibration signature is used to detect loose, worn, or unbalanced components. An unbalanced machine can occur for a number of reasons, including misadjusted components and product buildup. For example, the most common cause of increased vibration levels in fans is due to buildup of material on the rotating components. Oil analysis, or tribology, analyzes the oil used in the machine to determine the amount of particulates or the chemical composition of the oil. It is typically used to check the condition of gearboxes, engines, and hydraulic systems. Acoustic monitoring monitors the noise emitted by the machine. Loose, worn, or unbalanced components are the typical causes of vibration detected with this type of monitoring. Thermography checks the amount of heat generated by the machine. It detects problems such as excessive bearing loading and insufficient lubrication. Overall Equipment Effectiveness, or OEE, measures the success of a TPM program. OEE is a value expressed as a percentage that describes how productive a piece of equipment actually is compared to what it could be if operated at its maximum capability. By knowing and improving equipment effectiveness, a company can reduce losses due to inefficient equipment or processes. To determine overall equipment effectiveness, 3 factors are taken into account: equipment availability, performance, and quality rate. Describe how to calculate overall equipment effectiveness. Overall equipment effectiveness can be calculated by multiplying values for the 3 required factors of availability, performance rate, and quality rate using this formula. OEE is expressed as a percentage. The equipment's availability, sometimes called the operating rate, is the actual amount of time the equipment is available to operate when it is required to do so. Availability is expressed as a percentage and is determined using the availability formula. Availability takes 2 variables into account: total available operating time and actual operating time. Total available operating time is the number of minutes the machine could actually operate within the given period of time, usually a day. It removes any scheduled downtime, such as breaks and planned maintenance activities. The second variable required to determine availability is the actual operating time. It is determined by taking the total available operating time and subtracting out any unscheduled downtime, such as adjustments, changeovers, and breakdowns. The equipment's performance rate reflects how efficiently the equipment actually performs its job compared to how efficiently the machine is designed to perform. The performance rate reveals hidden losses due to reduced equipment performance. These hidden inefficiencies sometimes go unnoticed in production. To determine performance rate, 2 variables are taken into account: operating speed rate and net operating time. Operating speed rate indicates how fast a machine actually performs compared to how fast it is designed to perform. It is found by dividing ideal cycle time by actual cycle time. Ideal cycle time is the cycle time that would be achieved if the machine operated at its full design rate, and actual cycle time is the cycle time the machine actually achieves during operation. The second variable needed to determine performance rate is the net operating time. Net operating time is the percentage of time the machine operates at a constant speed without any interruption. It is used to determine idle times and minor stoppage time. Net operating time does not measure the speed of the machine, rather only if the machine is making products or not. Net operating time is determined by dividing the actual time the machine is making products by the overall time the machine is operating. The result is percentage of time that the machine makes products during operation and reveals the amount of time the machine suffered losses due to minor stoppages. Net operating time can be determined using the net operating time formula, and it is expressed as a percentage. The final variable required to determine overall equipment effectiveness is the quality rate. The quality rate is simply the number of acceptable products or parts produced by the machine compared to the total amount of products the machine produces. The quality rate reveals how often the machine produces a defective product or part. The quality rate is determined using the quality rate formula and is expressed as a percentage. The following is an example of how overall equipment effectiveness might be determined. The following information was collected from a piece of factory equipment. Total available operating time is 430 minutes. Actual operating time is 400 minutes. Ideal cycle time is 75 hundredths of a minute. Actual cycle time is 85 hundredths of a minute. Number quality items produced per day is 325. Number of defects per day is 15. Overall equipment effectiveness reveals problems that result in losses to the company. These inefficiencies can be classified into 6 categories based on the cause of the problem. These categories are referred to as the 6 big losses. A breakdown loss is a malfunction resulting in complete or partial loss of a machine's production. Breakdown loss is the biggest loss of the 6 types, and there are 2 types: function loss and function reduction loss. Function loss often occurs suddenly and prevents the machine from operating. Examples of function loss include a tool breaking or a burned-out motor. Function loss results in a reduced availability rate, which lowers overall equipment efficiency. Function reduction loss occurs when a machine still operates but at a reduced efficiency. It is often more difficult to recognize than function loss because the machine may appear to be operating at full efficiency. A machine may yield slightly fewer products per day because the rate of defects increases slightly and is only noticeable under close and continual observation. Function reduction loss affects overall equipment efficiency by reducing the performance rate or quality rate. Setup and adjustment losses refer to time lost due to setting up, retooling, or adjusting machines for operation. Setup and adjustment time is often required when switching a machine's setup to make a different product. Some setup and adjustment time loss is unavoidable, but practices should be put into place to standardize settings to minimize these losses. Setup and adjustment loss affects overall equipment efficiency by reducing the performance rate. Idling and minor stoppage loss, sometimes called small stops, refers to loss due to the temporary stopping of a machine to correct minor issues, such as a jammed part or safety sensors, preventing machine operation. These losses are easily fixed, but often overlooked. A company would study these losses to determine the cause and recommend a solution. Idling and minor stoppage loss affects overall equipment efficiency by reducing the performance rate by reducing net operating time. Speed loss is time lost by a machine that does not operate at its optimal design speed. Speed loss can be caused by mechanical problems, but is also caused by operators that intentionally slow down the machine out of fear of overtaxing the equipment or producing defective parts. This often results in speed loss being overlooked as a problem. Speed loss affects overall equipment efficiency by reducing the performance rate. Quality defects and rework loss. The time required to fix defective parts occurs when a machine produces defective products due to a mechanical malfunction. Quality defects and rework loss affects overall equipment efficiency by reducing the quality rate. Startup and yield losses, sometimes called startup rejects, occur when a machine produces defective or a reduced number of products during initial startup or the adjustment period. These losses often occur after changing over a machine to make a different product and are often difficult to identify. Startup and yield losses can be improved by standardizing startup procedures. These losses affect OEE by reducing either the quality rate or the performance rate. Describe a process for improving overall equipment effectiveness. Reducing losses and improving overall equipment effectiveness can help a company boost its profit. To accomplish this, a company must understand how each type of loss affects the overall equipment effectiveness and work to reduce these losses. Breaking down the OEE into its variables reveals where the biggest problems exist. By looking at availability, performance rate, and quality rate separately, companies can determine how each loss affects OEE. Consider the following example. A company has determined an OEE of 46 1/10% for a piece of equipment. In this example, it is easy to see the compounding effect that the low availability rate has on OEE, bringing it to under 50%. This occurs even though the performance rate and quality rate are reasonably high. In this case, availability has the greatest negative effect on OEE. To improve availability rate, the actual operating time must be increased. Since breakdowns cause a reduction in actual operating time, the team should investigate what is causing the machine to break down and eliminate the cause. It is important to determine the root cause of the problem rather than merely correcting the symptom. Otherwise, the problem may occur again. By understanding how each of the 6 big losses affects each variable of OEE, problems can be investigated and fixed. The chart shown here indicates how each of the 6 big losses can affect OEE. Applying lean manufacturing techniques such as Kaizen and 5S are often beneficial in solving problems with OEE. Kaizen calls for continuous improvement of processes. For example, a Kaizen event could be used to reduce setup and adjustment loss or speed loss. Breakdown loss is the biggest of the 6 losses because it results in unplanned downtime. Other factors cannot be addressed if the machine is not in operation. TPM puts an emphasis on trying to achieve 0 breakdowns. Implementing the following methods will help a company to achieve its goal of 0 breakdowns. Eliminate accelerated deterioration. Improve maintenance quality. Find the cause of the problem. Correct equipment design. And study each breakdown. Accelerated deterioration is equipment degradation that occurs from maintenance neglect and is the most common cause of breakdowns. Accelerated deterioration is eliminated by establishing basic equipment conditions, cleaning, lubricating, and tightening the equipment as necessary according to the manufacturer's recommendations. Accelerated deterioration is reduced by operating the machine as it was intended by not exceeding its maximum speeds, only using approved accessories, and following all manufacturer's recommendations. Maintenance quality can be improved by standardizing the way that equipment is maintained and by training the operators and maintenance personnel in the proper methods for maintaining the equipment. Improper maintenance can have as much of a negative effect on equipment as maintenance neglect, making maintenance quality an important aspect of eliminating breakdowns. It is important to investigate the root cause of the problem rather than simply fixing the symptom. Although fixing the symptom may be the quickest way to get the machine up and running again, it may only be a matter of time before the machine breaks down again, resulting in more downtime than if the cause of the problem were correctly diagnosed and solved the first time around. Weaknesses in equipment design sometimes result in chronic breakdowns. If the equipment design is the root cause of the problem, it should be investigated, studied, and possibly redesigned or replaced with equipment more suitable for the process. With each breakdown comes a learning opportunity. The company should work to determine and document the causes of each breakdown, the conditions under which the breakdown occurred, the maintenance procedures followed before the breakdown occurred, and the methods used to fix the problem. This information is valuable in adjusting maintenance and repair procedures to prevent the same problems from causing breakdowns in the future. Define autonomous maintenance and explain its importance. Machine operators are involved in any successful autonomous maintenance program. Autonomous maintenance is a maintenance program that puts the responsibility of daily maintenance in the hands of the machine operators. It reduces costs by freeing up maintenance personnel to focus on major problems, conducting equipment analysis, implementing new maintenance programs, and improving existing ones. Besides freeing up maintenance personnel, autonomous maintenance is also valuable because it gives machine operators ownership of maintaining their own equipment and helps them to better understand how their equipment operates. By participating in daily maintenance duties, operators are more able to notice an operating abnormality, making them more likely to notice and correct a problem before a breakdown occurs. Describe the elements of an autonomous maintenance program. An autonomous maintenance program unites maintenance personnel with operators in sharing maintenance responsibilities to keep machines working at optimal efficiency and eliminate breakdowns. It instills a teamwork mentality within the two departments. Operators become key players in maintaining their own equipment and helping maintenance and engineering personnel improve OEE. The maintenance department is essential in supporting the operators to use their machines with confidence and providing them with the necessary training and technical assistance. The autonomous maintenance concept makes operators primarily responsible for keeping their machine in optimal working condition. The operator's responsibilities can be broken down to three types of maintenance activities: preventing deterioration, measuring deterioration, and addressing deterioration. The most important responsibility for machine operators is to prevent equipment deterioration. The operator is responsible for several actions to prevent equipment deterioration. Early and prompt detection of abnormalities. Since the operator works most closely with the machine, he or she is the most likely to notice equipment abnormalities before a breakdown occurs, such as this puddle of fluid. It is the operator's responsibility to always be alert to potential problems to prevent breakdowns or stoppages. Establishing and maintaining normal operating conditions. Establishing normal equipment conditions results from cleaning and repairing equipment to return it to a state where it operates as intended. Maintaining those conditions results from the continual daily performance of tasks such as cleaning, lubricating, tightening, and checking. These tasks are the most basic and most important maintenance required to prevent equipment deterioration. Keeping maintenance records. The operator should maintain accurate maintenance records for the machine he or she operates. Accurate maintenance records are essential for preventing deterioration. Knowing past maintenance history can help predict future equipment needs, such as part replacements or fluid changes. If this information is not accurate, deterioration is more likely to occur. Correct adjustment. The operator must operate the equipment using the correct adjustments. This prevents quality defects and deterioration. Correct operation. The operator is responsible for operating the equipment correctly according to proper operation guidelines. This minimizes the chance of human error and prevents equipment. In addition to preventing deterioration, another AM operator maintenance activity is to measure the deterioration that has occurred so that it can be corrected. This is done by performing daily inspections of the equipment, including patrolling the equipment to look for any abnormalities and using the 5 senses during operation to help detect abnormalities before further deterioration can occur. Coolant level gauge. Hydraulic pressure gauge. Temperature gauge. Compressed air pressure gauge. The third AM operator activity is addressing deterioration. This includes performing minor servicing and taking emergency measures when abnormalities are discovered. Operators are also responsible for accurately reporting problems and abnormalities, and may assist maintenance in repairing their equipment after unexpected failures. Autonomous maintenance makes operators an effective part of the overall maintenance program, but it requires the support of the maintenance department. Some of the maintenance department's key activities in supporting autonomous maintenance are to provide instruction and training, deal promptly with deterioration, provide technical assistance in improvement activities, organize routine activities, prepare maintenance standards, build record-keeping systems, and develop failure analysis techniques. Describe how to implement an autonomous maintenance program. Companies have been successful in implementing autonomous maintenance programs using a step-by-step approach. The first 3 steps remove deterioration and establish normal equipment conditions. Step 4 and 5 train operators in general inspection procedures aimed at reducing breakdowns. Finally, Steps 6 and 7 strive to standardize and improve the autonomous maintenance system and instill the concept of self-management. Step 1. Perform initial cleaning. The cleaning phase removes dirt from the main parts of the machines and exposes defect sources, contamination sources, and inaccessible places. The cleaning phase offers many benefits. It restores the machine to normal conditions and prevents accelerated deterioration. It also helps the operators become more familiar with the equipment and develop a sense of ownership. Cleaning can also teach the operator how to recognize slight defects and other irregularities that may result in deterioration. Step 2. Address and eliminate contamination sources and inaccessible areas. During this phase, operators identify and eliminate sources of contamination on their equipment. They think of ways to improve parts that are difficult to clean, lubricate, or tighten. This phase improves equipment reliability by preventing contamination at its source. It makes it easier to clean and lubricate the equipment. This encourages the operator to develop other improvement ideas in the future. Step 3. Develop cleaning and checking standards. During this phase, the operator team develops work standards to maintain equipment at the levels established during the first 2 steps. The team decides what needs cleaning and how to clean it. The team also establishes standards regarding lubrication and cleaning methods. Equipment is modified with visual controls such as nameplates with lubricant type and quantity, proper gauge operating ranges, and belt specifications to make inspection easier. Step 4. Conduct general equipment inspection training. During this phase, operators are trained to inspect and maintain their equipment. They are taught general equipment functions, structure, and systems, and inspection skills through hands-on learning. Operators also learn to make simple repairs and the importance of recording inspection data. Step 5. Perform inspection autonomously. In this phase, operators combine the work standards and the general inspection knowledge taken from previous steps to create a formalized inspection process. Inspection tasks are divided into checklists, one listing those tasks handled by the operator and another listing those tasks handled by maintenance. This clarifies who is responsible for what and prevents some tasks from being duplicated while others are overlooked. Step 6. Organize and manage the workplace. In this step, operators take the easily understood standards they have successfully implemented with their equipment and extend it to other areas of production by applying similar standards to tools, materials, and processes. Work areas are organized and unnecessary items removed. Visual controls are applied to fixtures, measuring instruments, tools, storage areas, and others. Standards are created for changeover and setup operations. And Step 7. Carry out ongoing self-management and advanced improvement activities. Now, operators have the mindset of taking responsibility for their equipment and following self-implemented standards. During this step, operators strive to fine-tune processes, continuously looking for ways to improve. More data is collected and analyzed, uncovering additional areas needing improvement. Operators gain the confidence to develop ideas and are empowered to test and implement them. The goal of zero breakdowns begins to seem achievable. Cleaning is the process of removing all dirt, oil, grease, and other contaminants from equipment. In TPM, cleaning is a form of inspection used to expose hidden defects and return equipment to normal operating conditions. Inadequate cleaning methods can lead to equipment failure, product defects, accelerated deterioration, and speed losses. A successful TPM program includes regular and thorough cleaning. During the initial cleaning phase of an autonomous maintenance program implementation, operators clean their equipment until it is spotless. In Step 2, they eliminate sources of contamination and improve inaccessibility. During Step 3 of AM implementation, operators discuss the best methods and create standards and checklists for maintaining the equipment. When creating cleaning standards, teams consider several items. After deciding the best methods for cleaning the equipment, the operator team develops an easy-to-follow checklist. Using the checklist as part of the standard cleaning method, the operator is equipped to maintain basic conditions and eliminate accelerated deterioration. The checklist is broken down into several sections. After performing the initial cleaning phase, operators should devise methods to eliminate sources of contamination from inaccessible areas. The purpose of doing so is to reduce the amount of time required to perform cleaning operations. Two ways to reduce the time needed to clean inaccessible areas are to prevent the contamination from occurring in the first place and to make the areas more accessible. Contamination can be very damaging to equipment because it can result in a number of problems. One way to reduce the time needed to clean inaccessible areas is to prevent contamination from occurring in the first place. Leaky or blocked dust collecting ducts can cause dust contamination. Dry rotted hoses, bad gaskets, or loose connections can cause fluid leaks. The first step to preventing contamination is finding its source. Sometimes finding and correcting the source of the problem is an easy fix. Other times, it is an ongoing process to accurately determine the problem. In these cases, operators should localize and contain the contamination and try to reduce it by implementing a series of improvements that narrow down the problem to its source. Often these improvement ideas can be transferred to other areas with similar problems. Another way to prevent contamination is using dust-proofing techniques to extend the interval between needed cleanings. By taking measures like installing dust-proof covers over parts of the machinery that are not easily accessible, the interval between cleanings is greatly increased. The second way to reduce the time needed to clean inaccessible areas is to make those areas more accessible. Maintaining cleanliness will not last for long if cleaning the machine is dangerous or difficult. It is important to make cleaning as easy and safe as possible by making the machine more accessible for cleaning. Two methods that help improve accessibility are adapting equipment and adapting tools. Repositioning gauges, lubrication inlets, and other devices to positions that make them easier to use helps to reduce contamination and cleaning time. The equipment itself may be repositioned in a way that makes cleaning easier. Installing quick connect covers make accessibility faster, and repositioning attachments may provide additional space, making it easier to clean the equipment. Creating or modifying new tools designed to allow easier access to inaccessible areas may help reduce contamination. For example, a funnel that is shaped specifically for a piece of equipment may prevent spills during lubrication. Describe methods of developing and testing lubrication standards. Developing lubrication standards is an important method of improving equipment reliability and minimizing downtime. It is important that the standards devised make it possible to perform lubrication tasks quickly and easily, and that the operators performing the lubrication understand its importance. Most machine maintenance manuals specify a particular type and brand of lubricant to use. Although the type is important, machines can often use a different brand than the one listed in the manual if it meets the same specifications. Reducing the number of lubricants used within production wherever possible promotes consistency and reduces confusion. A diagram should be developed for each machine that clearly labels the position of lubrication points, complete with lubricant type and quantity to be used. Standardized labels should be designed and attached to the machine near lubrication points. The label should contain information about lubricant type and amount to use. This approach helps identify lubrication inlets when following an inlet diagram. Color-coding lubrication inlets are often used to indicate which type of lubricant is to be used. This is a good visual control that is easy to understand at a glance. Labels that show high and low lubricant levels should be clearly marked. A label indicating the machine's normal amount of lubricant consumption for a given period of time should be affixed to the machine as well. Standards should be set for the frequency and amount of lubricant to supply to each point on the machine. Too much lubrication can be as harmful as too little lubrication. For example, over-lubrication may cause bearings to overheat. If a chain oiler is set to apply excessive oil, it may drip from the chain onto the machine, creating a mess and attracting dust. Excessive oil added to a compressed air supply may cause downstream components to fail to operate properly. Good documentation should be maintained regarding lubrication history and standards. This helps to ensure that the proper lubricant is used and at the correct intervals. If any lubrication-related problems develop, the documentation can be examined for areas that may need to be revised. Over time, the lubrication standards can be fine-tuned. For autonomous maintenance to be effective, it is essential that operators thoroughly understand their machine. The operator is the first line of defense against breakdowns and efficiency losses. The more the operator knows regarding his or her equipment, the better equipped the operator is to detect abnormalities before a breakdown occurs. For this reason, proper training in equipment function is required. Before being trained in the specifics of running their machines, operators should undergo instruction in equipment subsystems that are common to most machines, such as lubrication systems, pneumatics, hydraulics, drive systems, controls, and others. In addition, personnel should be trained in fire prevention and other safety-related topics. General training is normally developed and delivered by the maintenance department, engineering department, or a dedicated training department that prepares text materials, diagrams, and other training aids. Training provides a good foundation for the operator to have a better understanding of how the machine he or she operates functions, and makes them more apt to apply the knowledge to better maintain their equipment. Effective training does not simply focus on theoretical knowledge. It provides the operators with hands-on knowledge. It is useless if the operator understands why something is done but does not possess the skills necessary to carry out the task. For this reason, good records must be kept of the training so that any inadequacies in theory and in practical ability may be addressed and corrected. Visual controls are any cue or indicator, such as color coding or labels, that helps personnel perform their jobs more easily. Visual controls are important because they reduce the time needed to maintain the equipment, prevent the operator from overlooking important maintenance tasks, and eliminate confusion over what maintenance should be performed. Visual controls make it easy to see when a problem occurs, allowing problems to be addressed before resulting in total failure. There are many types of visual control methods. Some general methods can be applied to almost every machine, but specific controls are often developed as the need arises. The following are examples of some visual controls applied to equipment and their subsystems. A common visual control that helps maintain the proper torque of bolts and reduces equipment vibration is using match marks on critical bolts. These marks are applied after torquing a bolt. It is easy to see that if the line does not go straight across the bolt head and onto the machine, the bolt has loosened and should be checked. Often, a different color mark is placed on bolt heads that the maintenance department is responsible for maintaining. Visual controls used on pneumatic systems commonly include flow direction arrows, marks on pressure gauge limits, labels on solenoids, and tube connections marked as inlet or outlet. Color coding can be used to differentiate pneumatic hoses from fluids being carried in other systems as well. Visual controls used on hydraulic systems commonly include pressure gauge limit marks, oil level and type labels, thermal labels on hydraulic pumps, and lock nut match marks on relief valves. Color coding is often used to indicate V-belt or chain types. Arrows often indicate the direction of belt, chain, or gear rotation. Peep windows are also often installed to allow for quick checking of belts without disassembling the machine. Color coding is often used to indicate V-belt or chain types. Arrows often indicate the direction of belt, chain, or gear rotation. Peep windows are also often installed to allow for quick checking of belts without disassembling the machine. A common visual control that helps maintain the proper torque of bolts and reduces equipment vibration is using match marks on critical bolts. These marks are applied after torquing a bolt. In an autonomous maintenance system, operators become responsible for cleaning and maintaining their equipment. There are 3 types of inspections required of operators: daily cleaning and inspection, patrol checking, and periodic inspection. Daily cleaning and inspection is the normal cleaning routine followed daily. Cleaning helps uncover minor defects and flaws and prevents accelerated deterioration. If an operator finds any abnormalities during daily cleaning and inspection, the problem is either handled by the operator or a request for maintenance is sent to the maintenance department. Patrol checking is the process of walking around the machine and checking visual controls to make sure that everything is in order. Patrol checking allows the operators the opportunity to check for abnormalities in parts of the equipment they cannot see from where they operate the machine. Often, a checklist that includes the path for the operator to walk around the machine is used to make sure nothing is overlooked. Periodic inspections are those done by the operator on a periodic basis, such as checking belts and chains, and others based on time intervals, usually every week or month.